Very good afternoon to everyone. Welcome back to Microprocessors and Microcontrollers, subject code 15CS44 for the Department of Computer Science and Information Science. This is module 5. We are discussing on the introduction to the ARM instruction set. My name is Harish V. Meekly, Assistant Professor, Department of ECE from BMS College of Engineering. We have looked into the syllabus. In the last class, we have stopped the discussion in between with the load and store instructions. This was the agenda for the last class. We had done the discussion on the load store instructions, single register load store instructions, indexing and addressing modes. So let's look at what the discussion that we have done in the last class for a few minutes and then jump to the today's lecture. This is a last class discussion, load and store instruction, single register transfer. What do you mean by load? Load operation is transferring the content from memory content from RAM locations to the register files. Store operation is copying the content of register files back to memory. And the memory is aligned, byte aligned. In this, like you can see the structure here. Together 2 bytes will be called as half word and the 4 bytes are called as a full word or 32-bit. And then we had a lot of different instructions in the load and store. 6 of them are unsigned instructions and 2 of them are signed instructions. We have done the discussion on the way the load and store instruction works. LDRH and STRH is for 16-bit transfer. LDRB and STRB is for 8-bit transfer. LDRSH and LDRSB is for LDRSH stands for load register sign half word. LDRSB stands for load register signed byte. And there are 3 indexing methods: post indexing, pre-indexing and pre-indexing with write back. Post indexing is by default always with a write back option. And there are some 3 addressing modes. These addressing modes in particularly are for mentioning this offset. In here, in the indexing methods, in the example to that, we have shown the immediate addressing mode only. In the possible addressing modes are immediate, register and register scaled. Register scaled is with barrel shifter operation. The table that is shown here is only for the post indexing method. The similar table or similar addressing modes are also applicable for pre-indexing and pre-index with write back options. And then we have done the discussion on the LDR and STR instructions with post indexing method. LDR pre-index and pre-index with write back. What is the difference? Register R0 address is not incremented if it is not a write back, if it does not have a write back option. The write back option is just an exclamatory mark at the end of the instruction. Similarly, store instruction with pre-index and pre-index with write back option. LDR instruction pre-index with write back using register and register scaled addressing mode. This was the last topic that we have discussed yesterday. Today we will start with load store instruction, that is multiple register load store instructions. For this, we will select the new presentation for today's lecture. Yep. So we have done in the syllabus, we have done the discussion till load store instruction, or we are still doing the discussion on the load store instruction. The part of it is completed. So this is what I said, like agenda for today's lecture: load store instruction, single register transfer instructions. In that we have discussed indexing and addressing modes in the single register transfer instructions. Today we will discuss on multiple register transfer instructions. Load store instruction, multiple register transfer instruction. Let's start with this. The advantage of loading and load store multiple values in a single instruction. The advantage of this instruction is we can load or we can store multiple values in a single instruction. But there is one disadvantage with this instruction. The disadvantage is that it increases the interrupt latency. Latency is a time duration between the occurrence of the interrupt and beginning of the ISR execution, interrupt service routine execution. Latency is a time duration between occurrence of the interrupt and the starting of the interrupt service routine execution. The time taken to start the interrupt service routine execution to the point that it has occurred, that duration is called latency. Once these instructions are executing, load, store, multiple values instructions are executing till that instruction gets completed, the interrupt service cannot be executed. Hence, this increases, or these instructions increases the interrupt latency. Now the syntax for this is instruction, CC, that is condition, addressing modes. This instructions also have a particular addressing modes for itself. We will see to that. Rn followed by an exclamatory mark and registers, the series of the register that we need to mention. In this, all of you know what is condition execution, conditional execution. The exclamatory mark also is known. The register Rn here is called as a base address again. Exclamatory mark indicates write back or update Rn address. If there is an exclamatory mark, then the Rn register value will keep on updating. If there is no exclamatory mark there is no write back or updating the register Rn value. The registers here, the series of the register can be mentioned as Rn-Rm in the flower bracket, not in the square bracket this time, it is in the flower bracket. Or we can also mention in the flower bracket Rn, Ro, Rp, Rm. So we can specify the series of registers with the comma separated registers, or we can specify them in the hyphen value. When we specify them a hyphen value, Rn should be lesser register value. That means Rn can be 1 or 2 and Rm4 can be like higher value than 1 or 2, that is R3, R4, R5 above this. So we will take an examples with this, so it will be more clear in the examples. And then what is the addressing modes that mentioned here? These addressing modes help to trace through the memory locations or the multiple registers. There are two instructions in the multiple load and multiple store. First one, LDM, that stands for load multiple words from memory into a register. Load the value from the memory into a register, and LDM stands for only a words transfer. STM, store multiple words from registers into a memory. This stands like what it says, store this register value into the memory. And all again, like to mention, both of these instructions are 32-bit operand instructions. In that addressing modes, what are the addressing modes that we had? Or what are the addressing modes that we have? We have these addressing modes IA. IA stands for increment after. IB stands for increment before. DA stands for decrement after. DB stands for decrement before. What is the significance of this? See to this store multiple and load multiple instruction. We can write the instruction like this, STMIA, that is store multiple register values, increment the memory location after storing it. STMIA stands for store multiple increment after. What is the meaning of this? Store multiple register values onto the memory and then increment it. LDMDB, what is the meaning of this? Load multiple register values from the memory and then increment the memory location. We will take the examples for particular to this addressing modes or these instructions, where in which it will be more clear. Before going to this, let us look at the this table again, the top table. When we say the addressing modes IA, that is increment after, the beginning addressing mode or beginning address for that register is Rn. the end address is Rn plus 4 multiplied by n minus 4. What is this? N is a number of registers that need to be loaded or stored. Rn is a base register. So if Rn is a base address, then like if there are 3 registers, then like Rn plus 12 minus 4, that is Rn plus 8. It will become Rn plus 8 because it is increment after. So it will load the value. If it will load the value and then increment it. One thing that we have to observe at the end is final value of Rn is Rn plus 4 multiplied by n. We will see this again with the example wherein which whatever the meaning of this will be more clear in there. But just for an understanding like what is the starting address and what is the end address, let's look at the table with 2 more or 3 more examples. When we say increment before, the beginning address is Rn plus 4. When we say increment before, the start address is Rn plus 4, the end address is Rn plus 4n. The final value of Rn, if we update with the final value of Rn with the exclamatory mark or write back option, then Rn plus 4n is an option there. DA is decrement after. When we say decrement after, please remember the start address is actually the decrement after is, the meaning is that like if we give the Rn as a base register, the end address will be Rn, the start address will be Rn minus 4n plus 4. The resultant address is Rn minus 4n. The decrement before, the start address is Rn minus 4n, end address is Rn minus 4. The total resultant value of the Rn at the end of this instruction, Rn minus 4n. We will look at these examples, like what is the meaning of exactly this start address, end address and the updated value of Rn in the next examples. Okay, before exactly going to the description with an examples, we will look at the memory first, or the way in which we will arrange the organize the memory. Let's start the memory location with 0x4 followed by 6 zeros or 7 zeros, which holds the 0th location holds the 0 0, first location holds 1 1. Similarly, cth location holds CC value. Let's store the first beginning address in the register R0, the last address is in the R1 register. Now with respect to this memory, all these memory values are 32-bit. So memory 32-bit 0x4 followed by 7 0. This memory location holds 33, 22, 11 and 0 0. That is from 33, 22, 11, 0 0. So this 0 0 is a LSB byte corresponding to this memory location. The remaining are incremented by one memory location. Totally 32-bit value formation for a register 32-bit value, 32-bit register. Next, memory one incremented value, that is plus 4 memory 0x4 followed by 604 will hold the value 77, 66, 55, 44, that is from here 44, 55, 66, 77. Similarly, like next 004 followed by 6 zeros and 8 location will hold the value from 88, and then like we will assume that like 0x4 followed by 60C memory location will hold FF, EE, DD, CC, wherein which only CC memory location or content is shown here. The remaining we have assumed that like after CC it is D, E, F memory locations, so that like memory content of those locations are DD, EE and FF. So this is the consideration for all the next examples or the upcoming examples. We will consider this memory structure. Right. Let's look into the LDM instructions. Before that, like we will start with this. R0 memory is 0x4 followed by 7 zeros. We have discussed like this is again from the previous slide. R1 0x4 followed by 6 zeros and C. R2, R3, R4 are registers which have the 0 0 values. Memory content of 4 followed by 7 zeros is 33, 22, 11 and 0. Memory content of 4 followed by 0x4 followed by 6 zeros and 4 is 77, 66, 55 and 44. Memory content of the next memory content is, that is 0x4 followed by 6 zeros and 8. Will have the memory content 0xBBAA9988. Similarly, C will have the memory location C, 4 followed by 6 zeros, and C will have the FF, EE, DD and CC. This is our consideration before the execution of the instruction. Once we execute each of this instruction, what will be after effect of this, we will see individually with the examples. Now look at the example 18. LDMIA, load multiple registers, increment after R0 with exclamatory mark, comma, R2, R4 in the flower bracket. Please remember, this is our flower bracket. In the previous example that we have discussed, it was square bracket. After the execution of this instruction, what happens in this instruction? The memory content pointed by the register R0, that is 4 followed by 70, that memory content will be transferred to register R2. It gets incremented, increment after is there. After that it will get incremented, then it will be followed by this memory location, which will hold the 77665544. That will be get transferred to R3 register. Next plus 4 value R0 gets incremented. After that, then it will become 0x4 followed by 008, 6 zeros followed by 8. The memory content of that gets transferred to R4. After that it gets incremented again, because it is increment after. So R0 value will be 0x4 followed by 6 zeros and C. So we'll just look at this instruction again. LDMIA, load multiple registers and then increment after R0 with exclamatory mark, comma, R2, R4 in the flower bracket, the range of these registers in the flower bracket. So from this R0 base address, the whatever the content of R0, that points to memory location, that memory location has the value, that value get transferred to the R2, first thing, then R0 is updated, next value, next memory location, then like that value gets copied to R3, again R0 is incremented, that memory location content is copied to R4. So 3 registers gets a value in a single instruction. 3 registers gets this value in a single instruction. This gets the value from the memory location in the RAM. That memory location address is pointed by R0. Hope this instruction is clear. With this clear understanding of one instruction or one example, the similar examples will fall in line. Let's see with example 19. What is this? LDMIB, R0 exclamatory mark with exclamatory mark, comma, R2 to R4, R2 hyphen R4 in the flower bracket. What is this says? Load multiple registers, increment before R0 holds the base address, then like R2. What happens with this instruction? Let's see if R0 is holding the value 4000 or 4 followed by 7 zeros. That 4 followed by 70 increments before copying the value to the R2 register. So R0 holds 4 followed by 7 zeros. It increments before executing the copying the value. That becomes R0 value becomes 0x4 followed by 6 zeros and the 4. Value of that location 77, 66, 55, 44 gets copied to R2. Then it increments to the next value, that is 08. Then it copies that value to the R3. Then again it increments by value by 4. This all increments by 4 because it is all like 32-bit operation or a word manipulation. So it is next value is 0x4 followed by 6 zeros and C. That holds the memory content FF, EE, DD, CC, that gets copied to R4. So in this instruction also, register R2, R3, R4 gets a value from the memory location which is pointed by R0, but only the difference is value of R0 increments first and then gets copied to the register, right? Similarly, look at the example 20. Example 20 is LDMDA R1 with exclamatory mark, R1 exclamatory mark, comma, R2 to R4, R2 hyphen R4 in the flower bracket. Now R1 address, what is the R1 content? Please look at that carefully. This is 4 followed by 6 zeros and C. Now what happens here is LDM DA, load multiple register and decrement after. So value of R1 is at the top of the memory location. The value of R1 that is 4004 followed by 6C, that content is FFEEDDCC, that gets copied to R4. This is what you mean by starting address in the previous slide. The starting address here is decrement after. Let's look at the previous slide here. The DA decrement after. The end address is Rn. The start address is Rn minus 4n plus 4. Please remember this. This is what we are discussing with the example there. LDM DA R1 exclamatory mark comma R2 comma R4. The R1 value is 4 followed by 60C. Now like that value will get copied to the R4. It decrements, then it becomes 4 followed by 6 zeros and 8. That value gets copied to R3. This value BBAA9988 gets copied to R3. And again it decrements by one more step. That becomes 4 followed by 6 zeros and the 4, 77665544. That gets copied to R2. Once it gets copied, then it decrements again because it is decrement after. So LDM DA, in this, if you check R1 value is 4 followed by 6C, 6 zeros and C. That value gets copied, or that value content is copied to R4 and then R3. That decrements and then it copies the memory content to R3. Then again it decrements, the memory location or address decrements, and then the content of that address is copied to R2. So the starting address in here will become 4000C minus 4n plus 4. That is the address from where R2 gets the value. The last value that is R4 register gets a address or a data from the memory location pointed by Rn or in this case R1 register. The same thing is mentioned in here. Decrement after, the end address is Rn. The Rn is the address location from which the last register will get the value. The start address means Rn minus 4n plus 4. This is address from the first register you will get the value. Hope this is clear now. The next one, example 21. Look at the example 21. LDM DB R1 exclamatory mark comma in the flower bracket R2 comma R2 hyphen R4. After what is the instruction, meaning of this instruction? Load multiple register, decrement before. That means whatever the content of R1 is there, that value address location gets decremented, or address value will get decremented, and then like the value content, address content is copied, and then it pushed to the R4, and then like to R3, then it gets again, address get decrements again, then it gets the value to R3, then address get decrements again, then it gets the value to R2. These three registers again R2, R3, R4 gets a value in a single instruction using like this. At the end of this instruction, the R1 value will be 4 followed by 7 zeros. The concept of this is same as the example 20. Now we will look the same examples or same with the same memory structure. With this memory structure, we will look at the store instructions. Store instructions, multiple store instructions. R0 holds the 4 followed by 60 location or 60 value. R1 holds 0x4 followed by 6 zeros and C. R2 holds the value 0x2 to 8 twos. R3 holds the value 0x8 threes. R4 holds the values 0x84. This is a assumption that we'll do, assumption that these registers will hold before the execution of these instructions. Similarly, the memory content is the same as the previous example. So let's look at the example 22. STMIA, that is store multiple registers onto memory, then increment after. Means what? Every time we store one register value to the memory, then we will increment the base address value. That is what is the meaning of increment after. R0 hyphen, the instruction is like this: STMIA R0 exclamatory mark comma R2 hyphen R4 in the flower bracket. R0 holds the value 0x4 followed by 60C. In this case, that is after the execution of this instruction. What happens in this instruction? Content of R2 gets copied to the initial address of R0. Initial address of R0 is 4 followed by 7 zeros. To for that memory 4 followed by 7 zeros, R2 value will get copied. That memory location gets incremented. That is what is meaning of increment after. That value gets incremented to 4, and then like memory location 4, and then like the value of R3 will get copied to this memory location. Then that memory location get incremented 4 followed by 6 zeros and 8. For that memory location, R4 will get copied to that memory location. This is an meaning, or this are the RAM memory location content after the execution of this instruction STMIA R0 exclamatory mark R2 to R4 R2 hyphen R4 in the flower bracket. If we understand this one example, the similar examples, the other examples will fall in line. So next example, example 23, STMIB, this is increment before R0 exclamatory mark R2 hyphen R4 in the flower bracket. After the execution of this instruction, R0 will be 0x4 followed by 6 zeros and C, because it loads a 3 value to the memory. What it has the instruction which is increment before, that is R0 value is 4 followed by 7 zeros, that gets incremented first, and then like R2 value goes to that memory location. Then like it increments one more time. Whenever I say increment, it is always plus 4 in this case, because it's a word transfer. So it will become memory location, or memory address will become plus 4, and then like R3 value will go to that memory location, again like plus 4, the final value of the R0 for there will the R4 value gets copied to that memory location. Now look at the example 24, that is STMDA R1 exclamatory mark R2 to R2 hyphen R4 in the flower bracket. In here, the R1 value is 0x4 before the execution of this instruction. R1 value is 0x4 followed by 6 zeros and C. In this case, it is store multiple register and decrement after. That is, store the value of R2 onto the memory location pointed by R1, then decrement, store the value of R3 onto the memory location pointed by R1, decremented R1, and then decrement again, then store the value of R4 onto the double decremented value from here. Every time when we say decrement, it is minus 4 here, because again it is a word transfer or word transfer. So memory location 0x4 followed by 6 zeros and the 4. This will have the 0x R2, that's 8 2's value, that is nothing but R2 value. Then like 8 will have the R3 value, and C will have the R4 value. Similarly, we have the last example in this discussion, that is example 25. Store STMDB R1 exclamatory mark comma R2 hyphen R4 in the flower bracket. What this means, store multiple register values onto the memory location pointed by register R1 and then decrement. What do you exactly mean by this? Copy the R2 value content to the R1, okay, decrement the R1 before, Okay, it's a STMDB, that is decrement before. Whatever the memory location pointed by R1, that value has to be decremented. For that decremented value, R2 gets copied. Then again it decrements, R3 gets copied. Then again it double decrements and then R4 gets copied. See to this what happens, R1 value will be, the final R1 value will be 0x4 followed by 7 zeros. For that value, you will store the 0x2 value. For that memory location, we are storing the R2 content. If you check the thing, what is happening here? Here it is happening that like R1 value, that is 4 followed by 0x4 followed by 6 zeros and C decrements before, that becomes 08. For that location, R4 value will get copied. Then it decrements, R3 value will get copied. Then it decrements, R2 value will get copied. Right. So point to remember here, the starting address, R1 address value here gets a value from R4 register. Then like decrements R3 register content. Then it decrements and then like R2 register content. Right. So that's about the multiple load and multiple store instructions. Now we look at the stack instructions. Stack instructions, all of you might be knowing what is stack. Stack is a memory in the memory location in the RAM, which is widely used for the contact switching. Whenever we call an instruction or whenever there is an interrupt call, then like stack memories will play a very important role. We'll discuss on that in a minute. Right. What is that ARM provides for the stack instructions? There are no specific stack instructions like push and pop in ARM. So ARM instruction set does not provide a specific instructions like push and pop like any other processor does. What it provides instead of that is LDM and STM instructions with the proper addressing modes. We'll see what do you mean by proper addressing modes in the next slide. But like let's look at this instruction. LDM and STM instruction with the proper addressing modes are used to do the stack operations. So there are no separate instructions. There are LDM and STM instruction itself will do the stack operation with the proper addressing modes. What are these proper addressing modes? We'll look at that in the next slide. Next point. Stack can grow up or down in memory. That is, stack can be ascending or descending. This is very important point. Let's look at the board for a minute. If this is the RAM location, let's say the one of this memory location, this is a RAM memory structure. One of this address value, the stack pointer is pointing. Now you can make the stack pointer to go up or go down. That's where the second point says stack can grow up. It can be grow up or ascending, or stack can also be descending or grow down. Right? Unlike there are many processors where in which stack will always grow up in the nature. Right? There is one more interesting point here. The third point, look at the third point. Stack pointer can point to last filled or empty memory location. In most of the processor, it is last filled memory location in the stack, wherein which the stack pointer points. In here, there is an option. You can make it to point to the last filled memory location or last empty memory location. Let's assume we have stored some value in the memory, that is 55, 44, 33, and then like if my stack pointer is pointing to the next free memory location, then we will call it as an empty. This is ascending This is descending. Now it is pointing to the empty cell or empty memory location. That's where the point says stack pointer can point to the last filled or empty memory location. You can make the pointer to point at 33 or the next memory location. It is an option. If it points here, then we will call this as an F, that is filled memory location. If it is pointing to the free memory location, that there we will call it as a E memory location. That is indicated by E. Please remember this. There are 4 things that to remember. Ascending, it can be stack can move, grow up or go down. When it grows up, we will say ascending. When it grows down, we will say descending. And then like we can make the stack pointer to point to the last filled memory location. If it points to filled memory location, we will indicate that by F. We can also make the stack pointer to point at last empty memory location. We can then indicate that by E value. Right? These are the 4 things that you have to remember. A, D, E, F in this thing. With this combination, we will see like what are the addressing modes that will get formed in the next slide. Now look at the last point. Monitoring the stack overflow or the underflow is a programmer's responsibility. In this processor also, the stack overflow or underflow has to be monitored by a programmer himself or programmer himself. Now, look at the addressing modes that are provided in the stack for the stack operation. What are the addressing modes? First addressing modes is full ascending, FA. FA stands for full ascending. This is where we have discussed with respect to the blackboard what it says. Stack memory location addressing modes is full ascending. That means stack pointer is pointing to the last filled memory location, and then the stack memory is ascending. It's growing up. So it is a combination of ascending and the full. That is why it is full ascending, FA. So with this addressing mode, now pop instruction means loading the memory value or like taking the stack memory values to the register, right? Loading the register values from the stack value or stack memory location is a pop. With that is done using an LDM FA. LDM is load multiple registers from full ascending stack. Full ascending. Hope this board gives you the clear understanding. This instruction LDM FA is very similar to the instruction LDM DA. What do you mean by LDM DA? Load multiple register decrement after. This instruction we have discussed with an example in the previous slides. So pop instruction says LDM FA. LDM FA instruction internally it works with the help of LDM DA. Now push instruction. Push instruction is that like you are pushing the register value to the stack memory. With that again like STMFA, that is full ascending stack. With the help of full ascending stack, store the register values and in the full ascending stack. That is the meaning of STMFA. This STMFA instruction is executed internally or like with the help of STMIB, that is store multiple registers then increment before. Store multiple registers and increment before. Similarly, there is a full descending stack, empty ascending stack and empty descending stack. So what you have to remember here is, you have to remember that like stack can grow up, stack can be ascending or descending. Stack pointer can point to the last empty memory location or last filled memory location. If you remember this 4 concepts, then like addressing modes understanding will be easy. And if this addressing modes understanding if you have this addressing modes understanding and LDM instruction with the LDM instruction with addressing modes understanding, then you will have a very clear understanding of full stack operations. We will see to the full descending stack operation, LDM FD. LDM FD is a pop instruction, that is load multiple register from a full descending stack. This is very similar to LDM IA, that is load multiple register increment after. Similarly, like LDM FD, STM FD, that is store multiple registers to the stack, and then which is very similar to STM DB, that is store multiple registers and decrement before, right. Let's look at the point here. What is the meaning of FA in the yellow color in the bottom, that if you can see there, F stands for full, that is stack pointer is pointing to the last filled or used memory location. A stands for ascending, that is stack memory can grow up in the memory. So that is the meaning of FA. That is what we have also discussed with the help of blackboard and the orally. Now the same examples that we have used for STM and LDM instruction in the previous slides will apply to the stack operation instruction. The only difference is, instead of using their LDM DA, here we will use LDM FA, that is all. If it is FA here, that means it is a stack value, stack operation. If it is DA here, it is a normal memory, normal RAM location. What is the change between this instructions and the LDM instructions and the stack instructions? Only the addressing mode and the base register in here is always a stack pointer. So rest of the things will remain same as for LDM and STM. So we will not discuss with the examples for this thing. The same examples will apply, same examples of STM and LDM instructions that we have discussed in the previous slides will also apply for the stack operation. The only change is the addressing modes and the base register, right. Next, look at this instruction, swap instruction. Swap is one more very special instruction of load store instruction. What it does internally, please look at this thing. The first point, these instructions exchanges a word between a register and a memory. So swap instruction will help to exchange a word between a register and the memory. This value will get exchanged. Now how value will be swapped, or it will be swapped. Very important point to remember, these are atomic operations. That means it cannot be interrupted by any other instruction. Whenever the swap instruction is executing, this instruction cannot be interrupted by any other instruction till it gets completed. In this swap, the syntax for the swap is this: SWP in the flower bracket B, again in the flower bracket there is a condition, then like RD, RM, Rn. There are two instructions available in the swap. One is SWP. What is that? SWP does swap a word between memory and register. The syntax for that is SWP R0, R1. This is an example, not a syntax. This is an example. SWP R0, R1, R2 in the square bracket. In such a case, what happens? Memory content pointed by R2, 32-bit value from the base address R2 gets copied to the R0, and value of register R1 gets copied to the memory content pointed by R2. R1 will remain as it is, it will not change. And this instruction is for 32-bit exchange or a 32-bit swap. The second instruction is SWPB. What is this instruction? Swap a byte between memory and a register. Swap a byte, not though the register is 32-bit, the lower byte gets copied to the memory, though the from the memory location pointed out by the register R2 here, that location value will get copied to the R0. See to this instruction SWPB R0, R1, R2 in the square bracket. What happens with that? R0 equal to memory 8-bit memory content of R2, that is memory location pointed by R2. From there the 8-bit is copied to the R0 value, and memory location pointed by the R2 register will get the value from the register R1. The lower byte of the R1 gets copied to this memory location pointed by R2. then again R1 will be unchanged. Let's look at an example which will be through which it will be more clear. Example 26, R0 value is 0, R1 value is 0x, 4 ones and 4 twos, R2 value is 0x, 4 zeros, 8500. Memory content of the R2 is 0x, 1, 2, 3, 4, 5, 7, 6, 8. Now look at the example SWP, now look at the instruction SWP, R0, R1, R2 in the square bracket. What happens? Content of R2 first gets copied to R0 and then like content of R1 gets copied to the R2 here. So let's R2 here in the sense R2 holds the address of the RAM location. That RAM location value gets affected with the R1 register value. Let's see what happens after the execution of this instruction. R0 will hold the value. R0 will hold the value of the RAM location pointed by the register R2, that is 1, 2, 3, 4, 5, 6, 7, 8. That's get copied to R0. R1 will hold the original value as it is. This R1 value will also get copied to the RAM location pointed by register R2. That's what this is the last point shows, or last line shows in the example 26. Now let's look at the example 27. In example 27, R0 content is 0, R1 content is 4 ones followed by 4 twos, R2 is 0x, 4 zeros followed by 8500. Content of memory location pointed by R2 is again 1, 2, 3, 5, 7, 1, 2, 3, 4, 5, 7, 6, 5, 6, 7, 8. That is very similar to the example 26. Now what happens with this instruction SWPB R0, R1, R2 in the square bracket. Content of R2, content of memory location pointed by register R2. In that content, the lower byte, that is 78, 78 gets copied to the register R0. With that 78, the remaining bits in the R0 is actually 32-bit register. In that 32-bit register, lower byte will hold the 78, remaining 24 bits will get updated with zeros. That means it is an unsigned operation. R1 will hold the original value as it is. Memory location 32 will hold this value. The memory location pointed by the register R2 will hold this lower nibble value, lower byte value of the lower byte value of the R1, that is 22. This 22 gets copied to the lower byte value. The remaining byte will remain as it is. There is a typing mistake here. So the memory 32 content, that is 0x, 4 zeros followed by 8500. The memory location, in this memory location, the value would be 0x 1, 2, 3, 4, 5, 6, 2, 2. This should be the value here, right? So this is a byte transfer, that is a word transfer. Example 26, word transfer or like word swap, and example 27 is a byte swap. There are only two swap instruction. This swap instruction, to conclude, exchanges a value from the RAM memory location to the register to the RAM. It swaps the content. Let's look at the last last in this. Okay. With the swap instruction, we have concluded the discussion on the load store instruction, right? Now we will look at one more instruction type, that is software interrupt instruction. For that, you have to remember this table. This is a vector interrupt table in the ARM architecture. In this vector interrupt table, software interrupt is at the memory location 0x08. Please remember this. Done? Now look at this thing. Software interrupt instructions are nothing but like software exceptions that provide some mechanism for calling an operating system routine. If there is an operating system routine or a function or a subroutine written, then like that has to be accessed or that has to be called, then you can use software exceptions to call that. Now every SWI instruction, now like software interrupt instruction, in here it is a SWI instruction. is associated with user defined SWI number. We will see what is this in the next slide. It forces, SWI instruction forces the system mode to change the system mode to supervisory mode. Normally the SWI instructions are used in the user mode. Now when we execute the SWI instruction, it will force the processor mode to go to supervisory mode. It also sets the PC value to 0x08. Now you know why 0x08 from the previous slide. Now look at the syntax. SWI software interrupt instruction with a condition. Okay, this can also be executed based on condition. Yeah, with SWI in flower bracket the condition SWI number. We will see the description of this. SWI is a software interrupt instruction. The example for this is SWI 0x123456 here. Once we do this, what happens? First thing that happens is current executing instruction or current PC value gets copied to the LR register, that is link register. So LR equal to 0x0004080004. This is a very particular example. Once if this is the current PC value, SWI instruction executed. After that, like there is an instruction to be executed. That instruction address is held in the PC. If that instruction address is 4 zeros followed by 8004, the SWI instruction address is 4048 followed by 3 zeros. The -4 value will be that value. CPSR content is new CPSR. It will get the new CPSR content, that is NZCV. All the flags gets copied from the supervisory mode. The present CPSR value gets copied to the SPSR, that is SPSR will get the CPSR values from the user mode. The PC value will be 0x0008 and R0 is 12. This R0 12 is the value that like 0x123456, this 12, whatever the number it has. Now at the last we will look at how does this interrupt is handled, or this the SWI instruction is handled. Once this instruction gets executed, once this instruction SWI 0x123456 gets executed, what happens? The first thing that happens is STMFD stack SP with exclamatory mark R0-R12 comma LR in the flower bracket. What do you mean by what is the meaning of this? Store the register content R0 to R12 and the link register onto the stack. So it will store this register value onto the stack. Next, LDR R10 comma LR comma immediate -4. That means whatever the LR register holds, that is present executing instruction address or next executable instruction address gets stored to LR as per our discussion in the previous slide. That -4, that means SWI instruction value gets copied to the R0. So what is this meaning? LDR R0 comma hyphen in square bracket LR comma immediate -4. Read the SWI instruction itself. That SWI instruction value gets copied to R10. Next is BIC, bit clear. This is, if you remember, the bit clear is it takes the NOT of this immediate value, then like ANDs with the R10 content. So R10 content right now it is SWI instruction. In that SWI instruction it masks the upper 8 bits. That is what is the meaning of this instruction. So mask of top 8 bits. Next, once this is masked off, the remaining bits will give us the value of the SWI number. With the help of that number, the BL service routine, branch with the link service routine, the service routine for this interrupt is called. You have to point to remember is R10 contains SWI number and branch to service routine with a link happens. Once this branch to service routine that happens, in there the SWI number is checked. Based on the SWI number, the particular task is done. Once that is finished, then it comes back here. In here what happens? LDM FD SP comma R0 to R12 PC. What it means? Return from SWI handler. That means whatever we have stored before handling this, whatever we have stored the register value onto the stack, now we retrieve those value from stack to the register, and the link register will get copied to the PC value. So this is how the software instructions get handled. So what we have studied in today's lecture, load store instructions, load store multiple register values. In that there is our addressing modes. Then we have studied stack instruction addressing modes, swap instructions, and then software interrupt instructions. Now if we look at all the 4 lectures, till here we have completed 4 lectures. In that 4 lectures we have studied in the classification till software interrupt instructions. There are 2 more classifications. We will discuss that in the next class. You can contact me for any clarification. You can contact me through my email ID or from my mobile number. Thank you so much.